Dear students, greetings of the day. In this lecture, we will discuss characteristic values and characteristic vectors of transformation as well as matrix. And in this lecture, we will discuss some definitions, theorems, as well as numericals. We will discuss characteristic roots and characteristic vectors of a matrix. First definition: characteristic root. Let T be a linear operator on a vector space Vf. Then a scalar lambda belongs to F is called characteristic root of T if and only if there exists a non-zero vector V belongs to capital V such that T of V is equal to lambda of V. Here V satisfying this is called characteristic vector and lambda is called the characteristic root. Another names are eigenvalue and eigenvector. For example, let D be a differential operator on vector space V, then D of e power 4t is equal to 4 e power 4t. This imply when you compare this with this, so here lambda is 4 and V is e power 4t. So eigenvalue is 4 and eigenvector is e power 4t. Next definition is characteristic roots and characteristic vectors for a matrix, that is definition 2. Let A be a square matrix of order n over F. Then a scalar lambda belongs to M F is called a characteristic root of A if and only if there exists a non-zero vector x, x1, x2, so on xn such that Ax is equal to lambda x. So to find characteristic roots and characteristic vectors, we will find characteristic equation that is determinant of lambda in minus a. The roots of this equation are characteristic roots, and then putting the values of roots here, we will get characteristic vectors corresponding. Now, first theorem. First theorem is, if T is a linear operator from V to V on a finite dimensional vector space, then every eigenvector of T has a unique eigenvalue. So we start by assuming let there are two eigenvalues associated with this eigenvector, that imply T of V is lambda 1 of V and T of V is lambda 2 of V. So as these two are equal, imply lambda 1v is equal to lambda 2v. So taking to other side, lambda 1 minus lambda 2 into v equals 0. As v is a non-zero vector, this implies lambda 1 minus lambda 2 equal to 0, which further imply lambda 1 is equal to lambda 2. Hence, every eigenvector is associated with a unique eigenvalue. So we prove non-zero eigenvectors v1, v2, vn corresponding to distinct eigenvalues lambda 1, lambda 2, lambda n of a linear operator T are linearly independent. So using the definition of eigenvalues and eigenvectors, we have T of v1 is equal to lambda 1 v1, T of v2 is equal to lambda 2 v2, and so on. T of vn equals to lambda n vn. So we have to prove v1, v2, vn is linearly independent. So we prove this by mathematical induction, and there are 3 steps in mathematical induction. Step 1, let n is equal to 1. So, and for n is equal to 1, we have just one element. So, and we all know that singleton set of a non-zero element is always linearly independent. The result is true for n is equal to 1. Step 2, assume the result is true for the number of vectors less than. Step 3, now we shall prove result for n vectors. Let linear combination of n vectors a1, a2, v2, so on, an, vn equal to 0, taking transformation on both sides, a1 v1, a2 v2, an, vn equals to t of 0, and which further imply as t is a linear operator which can be taken inside, a1 t v1, a2 t v2, an t vn, and image of 0 is 0. Now putting the value of t v1, t v2, t vn from here, so it is a1 lambda 1 v1, a2 lambda 2 v2, an lambda n vn, which imply, now taking this as 1, this as 2, now multiplying 1 by lambda n and subtracting from 2. So we get a1 v1 lambda n, a2 v2 lambda 2 lambda n, an lambda n vn equal to 0. So when we subtract, this will cancel out and we are left with a1 v1 lambda 1 minus lambda n, a2 v2 lambda 2 minus lambda n, an minus 1 vn minus 1 lambda n minus 1 lambda n equal to 0. So by step 2, result is true for less than n vectors. So all the scalars, that is a1 lambda 1 minus lambda n equal to 0, as well as a2 lambda 2 minus lambda n equal to 0, and an minus 1 lambda n minus 1 minus lambda n equal to 0. Eigenvalues are distinct. So a1 lambda 1 minus lambda n equal to 0 imply a1 equal to 0, as these two are distinct. So this implies all ai's a1, a2, an minus 1 equal to 0. Putting this in 1, so we get an vn equal to 0, and as vn is a non-zero vector, which imply an equal to 0. Thus we have a1 is equal to a2 is equal to an is equal to 0, which further imply all the eigenvectors are linearly independent. Next result, third one, 0 is a eigenvalue of t if and only if t is singular operator. So if 0 is a eigenvalue, by definition there must exist a eigenvector such that t of v equals to 0 into v, which is further 0. And we know that image of a non-zero element is 0. This implies t is singular operator. Number 4, if lambda is an eigenvalue of invertible operator t over the vector space Vf, so we prove that lambda inverse is eigenvalue of T inverse. So given T is invertible, and this implies T is non-singular. So imply there exists non-zero eigenvalue, and which imply lambda inverse also exists. Now as lambda is a eigenvalue, so there must exist eigenvector belong to V such that T of V is lambda of V. So as T is invertible, T inverse also exists. So operating T inverse on both sides, T inverse of lambda V. So on the left hand side we get V equals lambda of T inverse of V, which further imply, rearranging the terms, T inverse of V is equal to 1 by lambda of V or lambda inverse of V. That means lambda inverse is eigenvalue of T inverse.